Hello everyone, my name is Huanchun Chen. I'm from University of Texas at Austin. It's my pleasure to present our recent work Mixed Precision Quantization for Federated Learning on resource-constrained heterogeneous devices. We consider the federated learning framework in which client devices collaboratively train the global model by minimizing empirical risk without sharing their private data to the server. In the vanilla federated averaging algorithm, all clients are assumed capable of training and deploying a model with the same size, while in practice, an FL system may consist of devices with different resource constraints. Recently, there has been a growing interest in quantizing model into low-bit representation according to the memory budget so that the same model architecture can be deployed on different devices. While prior work in FL mainly focused on implementing fixed precision quantization, we formulate a FL problem with mixed precision quantization in which each client adaptively learns a quantized model with various bit width across layers without violating the constraints on the bit width budgets. However, the existing MPQ schemes typically train a full position model and then compute the quantization errors, which then used it to optimize layer-wise bit width allocation. Another family of schemes utilize reinforcement learning to search for optimal bit width allocation. Both of these two schemes require expensive computations and memory consumption, which are not practical for resource-constrained devices. We propose a novel method that automatically reduces precision of least important layers by performing sparsity promoting training without the help of a full precision model. Specifically, the server converts the weights of the global model into binary representation in B bits according to each client's budget Vn and sends the binary models to the corresponding clients for local training. While each client receives the converted global model from the server, sparsity promoting training is implemented on the private local data by adding a Gould-Lasso regularization term that measures the numbers of 1 in the binary weight B as described in the equation. The objective function enables each client to learn the local model that have a high levels of sparsity without causing significant performance degradation. Since the weights of the local models are discrete, we cannot directly compute gradients by backpropagation. Straight-through estimators enables a context network to forward pass intermediate signals using model parameters represented in fixed point format, while computing the gradients with continuous floating-point parameters as described in the two equations. Since the gradients computed from backward pass are floating points, we convert the weight updates into fixed point format using the power of 2 function and clip the update fixed point weights between the min and max values. After a client finishes local training, for each layer it computes delta L divided as the proportion of ones in the most significant bits of binary parameters in layer L. Then it proceeds by pulling the most significant bits if delta L is below some predetermined threshold value epsilon. Here, the figure is an example of pulling the MSBs in the BL, which are the binary weights in the L layers. Since the fourth and third bits in BL have the fractions of 1 below the threshold value epsilon, the bit width of the L layer is reduced from 4 bits to 2 bits. After local training, the servers then collects all the local models as well as the local bit width allocation from clients and computes them into floating point format. After that, the servers computes the weighted average of the collected parameters and the global bit width allocation. Before the servers converts the global models back into binary representation, the global bit width allocation is adjusted by the pooling growing algorithm while taking into consideration each client's budgets. In the experiments, we used the Dirichlet distribution to generate non-ID data partitions. Here, alpha is the concentration parameters controlling the level of heterogeneity. Moreover, in these experiments, we simulate 10 clients with various bit width budgets ranging from 2 to 8 bits. We compare our method FMPQ with the prior works implementing quantization in federated learning. Since there's no prior methods for misposition quantization in federated learning, we mainly focus on comparing FMPQ with AQFL, the first method to deploy fixed position quantization in FL. A part of the experimental results are shown in the table on the bottom. FMPQ outperforms the baseline AQFL by at least 3.2% and at most 9% in terms of the test accuracy with the same resources in the experiments on CIFAR 10, CIFAR 100, and Tiny ImageNet.